So I introduced this formula in class. We went through an example and just talked about it. We didn't actually do too much of it manually, but this problem's requesting it. So we're going to do this, and then we're going to jump to another problem that asks for some other information. But I'm going to try to explain standard deviation and what a z-score is in this video, and it might be long. Apologies. All right. In order to calculate the standard deviation, we need 3 different types of numbers. 2 of them are fixed, and one of them changes over time, and that's why, as I explained in class, there's this summation symbol, this sigma, capital S, Greek letter S. I believe it's a S. There might be more than whatever. So n is the number of values or number of data points or number of data or etc. So n in this case is 5. 1, 2, 3, 4, 5. X bar is the mean of those 5. So we need to calculate the mean in order to do that. This problem walks you through the whole process, first asking you to calculate the mean. So the mean of that, of course, is, and remember, X bar we use for the sample mean, and we use mu for the population mean, mu being a Greek letter. The population parameters are, we attempt to, or we try to be consistent in using Greek letters to represent the population characteristics, and not use Greek letters when we're talking about sample characteristics. I'll say, okay, so to calculate the mean, we need to add the 5 values together. When you were younger, you called this average, and then we divide by 5, which is the number of values. So really, we're summing all of the x sub i's when I begins with the first one and ends with the nth one, which is 5. So we're going to add the 5, x sub 1, x sub 2, x sub 3. I'll write it over again so you can see what I'm talking about with this symbology. This just says add x sub 1, oops, I wrote I, come on now, plus x sub 2, plus x sub 3, plus x sub 4, plus x sub 5. Hopefully, your previous teachers explained to you when I have a subscript, it's almost universally never doing any math. The subscript is just to denote one x value from another x value from another x value, and then divide by n. So I'm lazy. I'm a mathematician, so I'm lazy. I don't want to write all that, so I do this instead. The sum, where I starts with 1, ends with n. I could, for this specific problem, put 5 there, but I'm in the habit of writing n, so I can write anything after that. X sub I. So that's add all the x sub i's up and divide by n. That is the definition of mean, though it's never presented to you in that way. So we calculate the mean, which is, what is that? 28, 30, 40, 49, I think 54. Let's see, 54 divided by 5. Did I get 10.8? Yeah. So 54 divided by 5, which is 10.8. So I have x bar is equal to 10.8. Now down here, if we think about this symbology again, they forego writing the I and the n just for purposes. And so I'm going to take all the x's, I'm going to subtract the mean from them. So here, this is the x's. These are the x's, 14, 5, 9, 14, 12. This column, all we want you to do is write the result of taking x minus the mean. So 14 minus 10.8, 3.2. 5 minus 10.8. Notice it's going to be a negative number, negative 5.8. 9 minus 10.8, so that's negative 1.8. 14 minus 10.8, where do you have that? 3.2. 12 minus 10.8 is 1.2. Okay. Now notice some of them are positive or negative. Some of them are positive and some of them are negative. I'm going to draw a, I think, what will be a useful graphical representation of what's going on. Let's say that this line represents the number 10.8. So think of them as heights. And then I'm going to list this, like x-axis doesn't mean anything, so I'm just going to get rid of it. And I'm going to just list the values above and below. So 14 is 3.2 above. And let's see if I can position this so I can use the grid to my advantage. No, it's not wanting me to do that, I don't think. Oh yeah, maybe there. Okay. So I'm just going to put a value here. That's 10. Oh, well, that's stupid. If I want to use the grid, I want to make it easier for myself. That's 10 point, let's say it's 10.5, and let's say that that's 10.8. So 11, 12, 13, 14. So 14 is like here. I think that's right, 14. So 14 here, 13, 12, 11, 10, 9, 8, 7, 5, I think is the lowest one. Yeah. So here's 14. Then there's a 5. I'm just going to go over 2 units and go down to 5. And then I'm going to go to 9, 2 blocks over, and then represent the 9. And again, the horizontal axis doesn't mean anything. I'm just kind of looking just simply at the vertical. And then 14 again is up this way. So I'm going to have another 14 right here. And then I'm going to have a 12. That's 13. 12 is right here. Okay? Now, when we subtracted the mean, what we did was we got these distances. When I take 14 and I subtract 10.8, I get this positive 3.2. So the length of that white segment is 3.2. For the 5, we get this negative 1 because it's below that mean. It's below the mean. So it's how many units below the mean? Negative 5.8. And then when I see a positive number like this one, I know that that value before, even though I may not register the value anymore because it's gone, because I've turned this 14 into the number 3.2. Think of it that way. And but I keep the idea that I have numbers that are greater than 10.8, numbers that are less than 10.8. And then this last one is 12, and so that was what, 1.2. So now I've changed the values themselves into these differences from the mean, or these distances to the mean. Now, if I add all those numbers together, then I'll have some negative and some positive ones, and I'll get some number that is probably going to be below. What is that? 6.4, 6.6, 7.6, and negative 7.6. And so that's how we get the mean. Okay? The distances below plus the distance above are equal. And so we get 10.8. That's what we're doing when we're talking about average. We're like taking some numbers off the 14, some amount off the 14, and giving it to the 5, so they all collapse and they're all the same height. In fact, I think of taking the average of 2 bars. Like, let's say that this is the number 5, and this is the number 7. I think if I want to take the average of those 2 numbers, I add them together. 7 plus 5 is 12, divided by 2 is 6. But I think of it like this. I'm taking this box, and I'm putting it here, and I'm going to do that until all of the numbers are the same height. In this case, I only have 2 numbers, 5 and 7. But if I had another number, like 4, then I have to take, like, say, 2 of these off of here to get it to be this. And then I have to take this top one and divide it into 3 equal pieces. A third goes there, and a third goes there. That's how I think I'm okay at math. That's how I think of average all the time. When I'm walking around and thinking about the average, I'm trying to take the big numbers and chop off the tops and add them to the lesser numbers or the lower values until they're all the same height. This is another way of thinking about it. Is I'm going to get to this line in the middle where I've lessened the 14s until they go down, and the 12, and increasing the 5s and 9s. I only can increase them by the amount I take off the 14s and 12s until we get to the place that they're all the same level at this 10.8. Okay, so I've gotten these numbers. In this particular process, that the person, whoever it was, I never looked it up, who came up with the idea of standard deviation, they said, I don't want the negative numbers, or at least this is how I think of it. I don't want the negative numbers. I want to get rid of them so we can square them. And when we square them, all the negative numbers become positive because I'm multiplying negative times negative. Positives stay positive, so there you go. They all become positive numbers. So that's what this column is asking you to do. Take this number, 3.2, and square it. Take the column before this and just square the number. So what's 3.2 squared? Well, 3 squared is 9, so it's going to be somewhere between 9 and what would 4 be? 16. Somewhere between 9 and 16. We get 10.24. So I'm not going to do all that math for you. We're just going to list them out. So these are those distances squared. Then notice how this bottom one is saying, hey, take the sum of all those things. Well, those things are these 5. So we're going to take these 5 things, we're going to add them together, and we get that. Now, when we want to calculate the sample standard deviation, okay, on the slide, we didn't divide by n minus 1. We divided by n. And n was used, the n that we used in that was a capital N. So that is the population standard deviation. And we don't need to differentiate so much right now, but I'm trying to be thorough. Population standard deviation is this and the sample standard deviation, we have to change this to an S. We have to change this to an X bar. We have to change this to a little lowercase n and then subtract 1. That's the sample standard deviation. Okay, so this problem is asking you to calculate the sample standard deviation. I want to just focus on the process. So if I wanted to take this 58.8 and then essentially sort of take the average again by dividing by n. Now we have this little adjustment based on the fact that this is a sample, not a population, but don't worry about that little detail. Just think about, I'm trying to take the average again. I'm going to divide by n. So I'm going to take this 58.8, the sum that's in the numerator, and divide by, in this case, n minus 1. So 58.8 divided by 4 is going to be this, not this number. I got to do it because that's the total. So 58.8 divided by n minus 1, which is 5 minus 1, which is 4, and I get 14.7. So I get this is 14.7. That, in fact, is this before I take the square root. It's without the square root. I just did this stuff under here, and we get 14.7. At this point in time, 14.7 is the result of squaring these differences. And so when I take the square root to get standard deviation, I'm kind of like undoing that square thing. I'm sort of undoing that square thing. Yes, it's undoing the square thing of the whole thing, so it's not quite undoing it, but I'm sort of changing the magnitude of these numbers back to non-squared values. And so I take that 14.7 and I take the square root, and we get 3.83. And just to double check, where is that? I'm going to raise that to the 0.5. Hopefully you remember that from some previous class. 3.83 is my standard deviation. So take the square root of both sides, right? Square root. This becomes S. This becomes the square root of 14.7, and I get 3.83 as my standard deviation. Now, what does that mean? If my data is representative of the population, and we'll get to this later, if it's representative of my population, I can make some assumption that the sample standard deviation is representative of the population standard deviation. The population mean, the sample mean is representative of the population mean. So I can start thinking about the population as this normal distribution, and it has some mean, and that mean is at 10.8. And that sample, I'm simplifying it greatly. Okay, I'm simplifying it greatly, but for now, that standard deviation is telling you that the deviation from the mean is 3.83, and so one standard deviation is one distance 3.83 from 10.8. That's plus one standard deviation. And so I'm going to put another scale here. Extend this line down in orange. Instead of using 10.8, I'm going to put 0. And then that means that this is plus 1 standard deviations. I guess I should use S. You could use sigma too, because I'm saying this represents the population. The sample does not have that distribution because there's only 5 numbers. So that's why we often use sigma instead of S there, because that curve, that normal curve, is not a representation of the sample. So I'll leave it as sigma. If I go another 3.83 to the right, I will have another standard deviation to the right. And so that's plus 2 standard deviations. And if I go over a third one, another 3.83, then it will be 3 standard deviations. And you can go as many standard deviations if you want. If I continued this, this would be 4, 5, and 6. This is 6 standard deviations. There is a thing called 6 sigma, which is some usually it's associated with a very, very, very high level of quality, because you're getting rejections of some product at some tiny, tiny percentage, and that's way out here, okay? But that's not part of this course, so you don't have to worry about it. We can also apply the standard deviation in a negative direction. So I can go a standard deviation to the left of the mean, which would represent -1 standard deviations, or -1 sigma. I can do that again for a second standard deviation, and I can do it again for a third standard deviation. And remember, each one of these distances is in fact exactly 3.83 from the previous number as I go out. So in other words, I'm going to have to write this sideways to get the numbers in. 10.8 minus 3.83. Oh my goodness, that's going to hurt my head. I think I got 97 over here, and that's going to be 10. That's going to be 9 minus, I think I have 6. I'm going the wrong direction, you doofus. So this would be 6.97, I think. And I shouldn't have done that, should I? I don't want to do that. Here we go. 6.97. I'll keep subtracting. 3 is 3.14. And then I'm going to get some negative number. 83 is 17 is 31.31. I think that's correct. I'll check it. I'll check it very quickly. 10.8 minus 3.83. Pow. Minus 3.83. Pow. Minus 3.83. Oops, 6.9. Wow, I had a blunder. Serious blunder. 6.9 it was, huh? 6.9. Yeah, whatever. Okay, 10.8 is going to be 14.63, and then 18.46, and then 18, 19, 20, 21, 22. I think that's correct. And so I can look at this set of data, this distribution, this graph, as having these numbers or having these numbers. It does not matter. Okay? So now, I don't even know what this is. Let's say it's age of students who started playing the age at which students started playing the clarinet. I don't know, I'm making stuff up, right? Age at which students started playing the clarinet. And so if I said, oh, that's interesting. My niece, she started playing clarinet at age 13. Okay, I'm just trying to fit some scenario to this. Age 13. Maybe we don't need to do a second problem. We just work with this data. The question is where does she sit in terms of the population? Did she start very early? Did she start close to the average? Did she start very, very late? And remember, with the empirical rule, this region in between plus or minus 1 standard deviation is 68% of the population. That's a pretty large percentage of the population. 68%. If you said 68% of the people believe the same thing that you believe, and you would probably feel like, oh, I'm fairly vindicated. They believe the same thing that I do, right? If somebody said, yeah, 2% of the people believe the same thing that you do, okay. If you said, if someone said, your IQ test is in the 68th percentile, you nursing and medical majors, hopefully you know at this point that there is some question whether the IQ test is valid or not or whatever. But so I'm not really putting any clout, or I'm not touting the IQ test. I'm just as an example. But if you scored in the 68th percentile, you wouldn't feel too badly about that. It's above average, assuming average is 50%, right? And if the median of the populations that is close to, if it's a normal distribution, it's going to be close to the mean, so not too bad, not too shabby. You're in that center 68%. Or if you were in the 68th percentile, you would be, that's not 50, 60, 70, 80. This would be the 84th percentile, right? Because there's 50% here, and this is another 34. So this would be the 84th percentile. So my conversation about the 68th percentile. But I wouldn't still be too terribly sad about the 68th percentile, right? 84th percentile is even better. So if you were at this edge here, this upper edge, you'd be at the 84th percentile, which is not too shabby, okay? If my athleticism at my advanced decrepit age, as you can see me limping around, future classes, I had a problem with my Achilles. I was limping around all week. If my athletic ability was still at the 84th percentile, I'd be pretty happy at my age. So, if she started at age 13, what does that mean? Where does that, if we had this all graphed out, you could say, oh, well, that means that age 13, she was somewhere in here, right? She was somewhere here in this, where this blue line is. So she's within the larger population on either side of the mean. So she's doing okay. She actually started a little later than the average 10.8 years, but it's not too bad. It's better than certainly somebody starting at age 22 at 3 plus 3 standard deviations, right? But if we wanted to compare that, for instance, to another set of data, so I'm going to make up another set of data. I'm not going to put I'm going to try to put some numbers there, but let's see what we can do. Let's see if I can do this faster by copying this. Copy. Come on now. It's not letting me do what I want it to do. Let's try it again. Where's the duplicate thing? There it is. All right, let's see if I can do this without messing it up. Is that paste? That's duplicate again. Ugh, poopy face. Let's try it again. That's why I knew I was trying to do copy paste instead of duplicate. All right, copy. There we go. I don't know why it wasn't letting me paste before. Okay. So we're going to get rid of all these numbers because we're going to have a separate set of data. So what did I say? That was the age at which students started learning how to play the clarinet, I think I said. So now we're going to talk about trumpet players. When do people typically start playing the trumpet? And let's say that the average, I'm not going to make up any data points, so just make up the numbers. The average starts at 11.5, okay? But the standard deviation is, because of the trumpet lobby in Washington D.C., the standard deviation is only 2. So 2, 2, 2, 2, 2, 2, which goes to say that at 3 standard deviations, remember 3 standard deviations is 99.7% of those playing the trumpet started between age blah 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 and blah blah blah. So let's go figure out what that is. So 11.5 subtract 2, and I made it 2 to make it easier. Is 9.5, 7.5, 5.5, and then up to 13.5, 15.5, 17.5. Okay? So 99.7% of trumpet players start between the age of 5.5 and 17.5. But if we look at clarinet players, they start as early as negative 0.69. So they are still in the womb. I'm just kidding. That's just statistical aberration. This is going to happen. They start very young, and they'll start as late as 22.29 statistically. 22.29 statistically. So when I say that my nephew, he started playing the trumpet at age 13, okay? That's the same age that his twin niece, they're twins. I'm just making that stuff up. But they're twins, and they started both at age 13. Mom and Dad said, let's get them the hell out of the house and after school so we can drink wine after work. I'm just kidding. But sent the niece out to play the clarinet and sent the son, my nephew, the son out to play the trumpet. And so they're in band together and blah, 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 blah. But in terms of their ages, where does that fit? How do you compare them? As far as we know, they start at the same age, so they're fine. But in their respective communities or subgroups, the clarinet players and the trumpet players, one has a different or possibly an advantage because they're more, did they start closer to the mean or not? So are they closer to their peers in their experience or not? So we can use what is called a z-score to determine that. And if the z-score is closer to 0, that means it's closer to the mean because the mean is at 0 standard deviations. The mean is at 0 standard deviations. So how do we calculate a z-score? Well, we simply take, well, let me do this for you so you can, because I don't know if is it in the slides? I can't remember if it's in the slide set or not. So I just want to show you how to look. I just want to make sure I'm reinforcing the idea that you can look stuff up and stuff is in the information that we've given you. I think it's all the way near the bottom, if it's in there at all. Yeah, so there's a z-score there. I believe that's what we're doing. That's what I'm recognizing here. John has the better GPA when compared to schools. Yeah, because of two different schools. So what we're going to do is we're going to figure out what the z-score for my niece, let's call this ZN, and that's going to be her age, instead of GPA, it's going to be her age, 13, minus the mean. Like I said, mean of the population. We believe this sample represents the population, so we're going to say 10.8. And we're going to divide it by the population standard deviation, which we're using this 3.83. So what we're doing is we're taking 13.8, subtracting the 10.8, and dividing it by this 3.83. We are essentially doing what I would call is we're normalizing this 13. The 13 doesn't mean anything on its own. But based on how clumped together or how the population behaves, we can figure out where it exists along this continuum, this horizontal axis. Where does it sit? How many standard deviations away? And so 13 minus 10.8. And then I'm going to divide all of that by 3.83. And her z-score is 0.574. 0.574. Which my blue line here is not too far off. 0.574. Now, how does my nephew compare? Because there are two different populations with two different information, and this little problem, the example problem, is trying to show the same thing because these two students, Allie and John, are in two different schools, right? To his school, blah, 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 her school, okay? We're going to take, what did I say, Z of niece, so this is nephew. Oh, I got to put P or something, I don't know. They both start with N, you doofus. Not you guys, of course, but me. We're going to take his value, 13, which was the same, but remember, his mean is different, and his standard deviation is different. And so we got 13 minus 11.5, which is 1.5. Divide that by 2. And so we get 1.5 divided by 2, and we get 0.75. So his z-score is 0.75, which kind of means that he's further away from the mean. He's further away from the mean than my niece. So in fact, my niece is closer to the mean. She's closer to her peer group with regard to where she started her process in learning the clarinet than him learning the trumpet. Even though his number what was it? This number is 1.5 and hers was 2.2, I think. Yeah, 2.2. So she's even further away from her mean just by subtraction, but because the standard deviation, everyone's more spread out, she's actually in a better position. Okay? So all of this information can tell us something. The z-score allows us to compare what's happening between two different groups, and we can do some comparison. At least that's how I think of the z-score. Okay? Difference in calculating z-score. Here's if we're doing it with a population. This is if we're doing it with a sample. Remember, population uses Greek letters, and the sample uses those non-Greek letters, x bar for mean and s for standard deviation. Here, I don't know what that is. And then this is where we were at. I think we're up here further. Yeah, and there's their standard deviation. Now, I didn't talk about this. This number, when we take the standard deviation and square it, I had it up here, this s squared. That number is called the variance. That calculation is called the variance. And we don't need to, I will type it in, variance, so we can get a definition for you. I think I like this way it's written. It's the expected, is that what we want? It's the expected value of the squared deviation for the mean. Yeah, that doesn't really help you. It doesn't have, let's see if we can do this. Lay person explanation of variance. Let's see if this will do a better job for you. Intuitively, yes. So this is somebody asking on, what is this, Stack Exchange? Yes. What is the cleanest, easiest way to explain some of the concept of variance? Okay. Same one asked last year. Somebody asked last year. Okay, I would probably use a similar analogy to the one I've learned to give lay people, that's just normal people like me and you. When introducing the concept of bias and variance, the dartboard analogy seen below. Bias variance, we don't need bias variance, you doofus. Why is this person didn't ask about bias variance? They asked about variance. Let's see what he says. Bias variance decomposition is like trying to hit the bullseye on a dartboard. Each dart is thrown after training our dart throwing model in a slightly different manner. If the darts vary wildly, the learner is high variance. If they are far from the bullseye, the learner is high bias. Oh, okay. All right. That's why they're bringing the idea of bias in. Oh, you science people. It's kind of like talking about the difference between accurate and what's the other thing? Accuracy and what was that? Accuracy comes up when we're doing significant figures. Accuracy versus precision. You may have remembered that discussion. Accuracy and precision. Same thing. Accurate and precise. Accurate but not precise. Not accurate but precise. Precise being all grouped together but not where you want it to be. Grouped all different ways, different separated from each other. That's not very precise, but you're close to the desired goal, so that's all accurate. Not accurate, not precise. You're all over the place, and you're not really close to the desired goal. Again, precision is you're consistently hitting the same spot. You're just hitting the wrong spot. Accurate and precise, you're consistently hitting the correct spot, and you're consistently hitting a spot, and it is very close to the correct spot. And so I think this person's making the same argument. Yeah. High bias and high variance. Low bias, high variance. High bias, low variance. Low bias, low variance. So they're associating, this person's explanation is associating variance with precision. So variance would be the difference, it's the opposite direction of precision. Oh, come on. right? Because if we're precise, we're grouped closely. If we're variant, we are not close together. High variance, far apart, high variance, far apart. So it seems as if somewhere somebody determined that variance and precision are sort of opposite ends of a spectrum or a continuum or something like that. In any case, if the variance number is lower, we are more grouped together. And if the variance number is higher, we are more spread apart. So I'm going to end the video now because it's already super long. It might be well over 20 minutes, 36 minutes. So there you go.